At the end of the last lecture, we showed that, well, you showed that proofs this guy same as so these are Hodge groups that discuss the number of harmonic p-forms, and p-forms it's a vector space that has a dimension. This was supposed to be a space of closed forms, not modulo exact forms, so closed forms of degree p modulo exact forms of degree p. And they're isomorphic as spaces, in particular their dimensions are the same, so we'll do the real dimension of either one of these two. It doesn't really matter which one you take. And this is the P-Betty number, which we also saw as coming from a different source, which was through the homology theory. One thing I didn't prove, and I should have done at the end of the last lecture, except I was already in minus 10 minutes, I think, so stop, is that we have the star operator. So we have, let's work with differential forms and take X to be a Riemannian manifold, so I can actually work over there. And so if omega p is in H p delta, remember delta by definition is delta v plus p delta, and we also know that this is true. Did I get you to check this? I didn't ask you to check it. Great, that's our first homework. Please check, it's easy. Easy. So if it's looking hard, then you're not doing it right. So star commutes with the LASS. So using that, we have the following, which is that if delta Wp is equal to 0, that obviously implies that star Wp is equal to 0. I can take it through, and therefore I just straight away get this. Where does this live? Star of omega p lives. It's an n minus p form, right? So this is actually a harmonic. And so remember, star is an invertible map. So what we've just given is a map between harmonic p forms and harmonic n minus p forms. So we've just shown the following: H p delta of x is isomorphic to H p n minus p of x. Just shown that. And for free, once you've got that, the dimension of this space, if they're isomorphic, these are vector spaces, the dimension of this space must be the same as the dimension of that space, which tells me that bpx equals bn minus p of x. Right? So the Betty numbers of my manifold satisfy this relationship. So now we have a lot of stuff. We've got Betty numbers kind of count, p-dimensional submanifolds. They count sort of how many independent ones you've got. They count the number of exact versus modulo coexact forms. They count the number of harmonic forms. Okay? So we've got many descriptions of these numbers. And the reason I'm wasting your time with these numbers is because what I'd really like to talk about is something that string theorists would like me to talk about, which is fluid supply. Okay, now we saw in Barton's course that the world is 26-dimensional. We had a small refinement on that from Carmen's course. She told us, that's not true. It's actually 10-dimensional. Now, I don't know about you guys, but for me, the world is 4-dimensional. Well, it depends on how much I've been drinking. But anyway, it feels like 4 dimensions most of the time. So what we need is a way to get from 10 or 26 or whatever, let's do this generally, what we need is to get from some higher dimensional space to the one we live in. Of course, if the universe is 10-dimensional, then we live in that one, but I mean the 4 dimensions that we see. So I'm going to start off with product manifolds. And take the attitude that my space is actually the one that I'm interested in living in times something else. And I don't know, well, this is true. The real dimension of x is actually equal to the real dimension of m. Who did that? Sorry. Plus the real dimension. Okay, so here we've got a chance. If we start off in, as an example, if we start off in 10-dimensional string theory, then what we'd really like to do is to write 4 plus 6. Okay, if you're having a hard time with that. But it doesn't have to be 4 plus 6. This could be 26, and then it could be 4 plus 20, for example. All right. And in a sense, the only way that's going to work is that if k is small, k is small will mean that somehow the ratio of the volume of k to m, or some way of measuring things, is small, okay? So that's what we'll mean by small. I'll be a little bit more precise when we get to it. All right. What we've learned in recent years is that K doesn't have to be compact closed, but for the purposes of these lectures, I will take that as given. So for us, K is a compact closed. Closed means no boundary. Manifold. So that's nice. That's one way to get around the 10-dimensional problem. But you have to ask yourself, if there is such a small space, if I start off with 10-dimensional string theory, and I say, well, that 10 dimensions is really the space I'm interested in, producted with this small space, can this small space affect the physics that I see, that you see, in this lecture room? So that's the question, right? And the answer is, very strongly, yeah, it does. It really strongly affects the physics. And that's what we want to discover now. So I'll start by some notation. So for me, M is Minkowski or Euclidean, but you can do the Euclidean case. And K is definitely Euclidean. here I mean that the signature of the metrics that I'm using on these spaces are of that type. So if again, because string theory is the driving force behind these courses, string theory is on a 10-dimensional, Kalman's string theories are on a 10-dimensional manifold with Lorentzian signature. Space-time has a Lorentzian signature, therefore overall I want to have whatever metric I put on this thing to have one Lorentzian signature. And if you're obtuse, you can have more, but I don't want that, I just want one. So this guy carries the negative sign in the metric. Okay? And that means that guy doesn't. Local coordinates, so on my big space, I'll write them like this. This is supposed to be Greek mu, black 9. And so again, these are quite general, but for the sake of argument, if m is equal to 1 dot 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 to 10, that's not very good, is it? Who did that? Sorry. 0 to 9, then x mu is, sorry, mu is 0 to 3, and I is 4 off to 9. Okay? They're the local coordinates. 10-dimensional space needs 10 coordinates locally. These are the ones. So, in general, if x is d-dimensional, no, so as I said, I'll actually say what I mean by small in a little while. But yeah, so somehow you just don't want to see it. You want to be able to use a meter stick, and you want that thing to be 10 to the minus 500 centimeters in length, or its volume at least is something tiny. But that's not the way I'll do it. I'll give you a different sort of definition. Thank you.
George?
Yeah.
Sorry, there is a dynamical way to get data composition. Is there
A string
oh,
theory?
so far.
String theory? Not that I know of. So no, this is you do it with these things by hand.
Matrix theory? Matrix theory?
Yeah, no, I think there are already too many choices. You have to make choices, so it's not really. I mean, in string theory language, the thing that you get is actually just a bunch of moduli. So these two are moduli in a sense. So you have to find some way, as you were saying, the dynamics to land on the right thing. I have no vested interest in this, but I know there are many camps, so I'll stay right out of that one. Okay, so, and if the dimension R of M is the one I want to be D, yes, be little d, and the conservation rule tells you that the dimension of K is just the difference in the dimensions, right? So we'll start like that. But in particular, we have to worry about the Lorentz group. This is something that Nathan was insisting on quite heavily when he was talking about the creation of spinors and stuff. You really have to be very, very careful about what the Lorentz group is up to. So the Lorentz group, local Lorentz group at least, for a d-dimensional manifold of Lorentzian signature 1 is d minus 1, 1. Inside that sits my favorite Lorentz group, which is the one which comes from here, which is d minus 1, 1, and it's a group product with the Lorentz group of this guy, but the Lorentz group is really the Euclidean group, so d minus d. Okay? So these two live in there. Any object, any tensor, any spinor, any duck, it doesn't really matter, anything that lives on this space has a decomposition under these guys, right? SO at d minus 1, 1 mixes these things up. at least the tangent spaces of these things are. These guys are the ones which preserve the structures on M, and this guy is the guy who preserves the structure on K, just mixes K with itself. This chap just mixes the stuff on M with itself, right? So these are once we've taken the product manifold, we want to think of it as a product manifold. It's this group that we're interested in more than this group.
So it's not B minus 1, comma 1. It's a symmetry of B-dimensional incosity. But
Yes.
But our B-dimensional space is not incosity.
This
So
one?
what it is required that this subgroup be a subgroup of SOB minus 1.
This one here?
Yeah, this is not incosity space.
No, but yeah, okay. Locally, it's like this. And if you want a more invariant way of saying it, I think the right thing to do, I'll write something up here so I can maybe. All right, so let's take a vector. I can always write a vector using an n-bind, and the group which is relevant for the n-binds is that group. So I can do that for any tensor, and as you saw, this is actually essentially what Nathan was really doing.
It's local, local.
The local Lorentz group, yeah, exactly. But local Lorentz is really just another way of just saying that if I just look at a local part of the manifold, then hey, it's like, thank you. Okay, so anyway, these are the groups which are of interest to us. So part of our job is if I give you a tensor, whatever it is, tensor, spinor, whatever it happens to be, so one, decompose it so it's a tensor spinor in 10 dimensions, but at the minute I'm going to play this game, I have to tell you what it is with respect to these groups. Okay? So that's part of the game. Decompose under these. I'll be very specific about it in just a tick. And number 2, physics on M. As you've noticed, most of my first two lectures had nothing to do with what you would have called physics, right? So we now need to go to our sponsor and do some things. Okay, so here's the prime example that you all learn, which is, I'm going to consider maybe let me do the decomposition first, and maybe that. All right, let me do the decomposition because I think it will help. Suppose I have a scalar, so let's start with number 1. Forget my notes, you're not going to get them for a while anyway, so. Let's just start with the scalar. I have a scalar in 10 dimensions, or a scalar in d dimensions, big D. So phi is a scalar of SO d minus 1, 1. What does a scalar mean? It's invariant. It doesn't change. Right? It just sits there, like that. And SO d minus 1, 1. Now if it's a scalar, and it doesn't change, and this is a subgroup of that, it's going to change under this? I think so. It's going to change under that? Nah. So this is a scalar under SO d minus 1, 1, and a scalar SO d. So as far as a scalar in 10 dimensions is concerned, it is a scalar on M and on K. Well, that was easy. Let's try vector. Big N label, because I told you that my labels are going to be big N on the big space. This guy I can write as this chap. Right? It has components like that. It's a vector. Well, actually, this is the basis of one form, but you don't care. It's a vector. Right? So, question. Under SO big D minus 1, 1, this transforms as a vector. Right? Fine. So, it's whatever it is. Under SO D minus 1, 1, this carries a vector label, right? These are the labels for these guys. So this is a vector of SO D minus 1, 1. Does it carry a label of the space K? No, it doesn't. So it can't transform, can it? So it must be a scalar. So this is a scalar. Now we play the same game with this guy. This does not have a mu index, so it must be a scalar of n. So scalar of n, that chap. And on the other hand, it does carry a vector label of k, so it must be a vector. And so you can already see things are a bit peculiar because from my point of view on my space-time, what was a vector in 10 dimensions has suddenly become a very strange thing. It's become a vector and a bunch of scalars. For every value of I get a scalar. Okay? So already something odd is happening from my lower perspective. How about an antisymmetric 2 form? You've probably noticed that these things are things which appeared in the last lecture. Right? So let's keep going. BMN is an antisymmetric 2 form, so now I can write that as an antisymmetric 2 form as far as M is concerned. So antisymmetric means, of course, that this is minus B. You can do the symmetric case too if you like, it doesn't matter, but this is what we need. Then we can have a thing called B mu I, and then we can have a thing called Bij. Now because this guy is antisymmetric, okay, these have to be antisymmetric when I exchange them. These have to be antisymmetric when I exchange them. These I don't exchange. I don't need to know what B I mu is. I just deal with B mu I forever. Okay? Don't worry about B I mu. Finished. B I mu is minus this. But I don't need that. I'll stay with this. Okay? So now, let's play the same game. This is, as far as M is concerned, this is antisymmetric, right? So this is antisymmetric tensor. On M. What is it on K? Scalar. How about this guy? As far as M is concerned, the I label doesn't mean anything. So this is a vector, so say a 1 form on M, and simultaneously, as far as K is concerned, the mu label doesn't mean anything. So simultaneously, a 1 form on K.
Sorry. Okay, this is not really a scalar or a 2 form because you have labels of the other space.
Sorry?
You have labels of the other space. In general, it depends on also on.
Yes. I'll get to that. I'm just asking how the global group transforms. I mean, yes, you're right. But this is just to give you an idea of the fact that these things split in this way globally. Okay, so, and likewise here, this is a 0 form on M and a 2 form on K. Now all your physics you see from what happens to you from your M perspective. Okay? You see from your M perspective. So from your M perspective, you have a 2 form. You have a whole bunch of 1 forms. You don't, I mean, the I just labels other things for you. You have a whole bunch of I forms, of 1 forms. And here you have a whole bunch of scalars from your point of view in M, your physics in M. All right? Is this clear?
Not very well.
Which part? And if you say all of it, you're in trouble.
No, the last part.
Sorry. The last part. So from the point of view of M, right? This is a 2 form. Fine. From the point of view of M, this is a 1 form on M, and for each I. Because M doesn't care about I's. This is just some external label counting the number of 1 forms that I have. That's right. Well, I'll show you in a tick that this naive statement is naive, but close enough. And likewise here, for every possible ij which is allowed, it's antisymmetric after all. If I was, I don't know, in 6 dimensions, this would be 15 of them. They would all be scalars on M. I'd end up with 15 scalars on M. Okay?
Okay.
All right. So something that starts off as 1 object in 10 dimensions breaks into a whole lot of bunch in 4. No.
Dij is a form on K that is also antisymmetric. That's the question.
The 2 form is antisymmetric.
Ah, okay.
Yeah, you're right. So thank you. That's fair enough. If I was really to write it as a form, what I would have to write is Bij dyi wedge dyj. And this guy's antisymmetric. The only component, see, this has to be antisymmetric because the only thing here is this is antisymmetric, so nothing else survives. Okay. I learned that you're allowed to use any language you like to do these lectures in. Is that true? So, dus, ik zal mijn Nederlands proberen. Which means I'm going to try my Dutch, of which I'm now exhausted. Okay. So, that's roughly picture of what happens with the groups. So this is how they decompose. Well, what is really going on? So let's have a look. Give an example. Here's the example. Read if I write here. I'll take that as a yes. So this is the typical example, and I like to call it massless on X, but massive on N, question mark. So the manifold I'm going to take is K is just some S1. Just a circle. So that means X is equal to M cross S1. This is the traditional example of Kaluza-Klein. And I'm going to be very finicky. That is, I'm going to consider a metric on this space, ds2, which is actually g mu nu. And I'll explain why as we go along. Mu tensor is nu plus r squared d theta. Theta. So, look at what I've done. First, I've said that this is really a product manifold, and the metric that I'm going to choose does not mix things, so there's no dx d theta term here. Okay. And I've said something stronger. I've said that g mu nu of x is not a function of theta. All right? So the metric that I have here doesn't really depend on where I am on the circle. Okay, so I've taken a real product metric in that sense. R is of course nothing more than the radius of the circle. So the volume of S1, so let's calculate the volume. This is the integral from 0 to 2 pi, d theta root g. G theta theta is just r squared. The determinant of g theta theta is g theta theta, so that's still r squared. The square root of the determinant is r. Remember, you're always taking the positive root when you take the root. So this is just r, integral 0 to 2 pi, theta. Whoa! Okay, we can go home because that's a great result. So you can tell why I chose r squared there. If I chose 2r squared, we've got something different. All right, what about the Laplacian on x? Well, these spaces don't mix, right? These spaces...
What's the square root of g?
G.
Are you talking about the metric on M?
On S1. Volume of S1. So this is just theta theta, which is just that.
Yeah.
Okay, so what's the Laplacian on this space? Well, you've taken a metric which is really, splits, right? So if you remember, that really means that the Laplacian that you have is the Laplacian on M plus the Laplacian on S1. The metrics don't talk. So whatever I do to create the Laplacian, it must actually just split this way. So I'll take this to be, well, just that. And this is just minus 1 over r squared. Who did that? Remember that the Laplacian is made roughly from G, Mn, Dm, Dn, right? So G, Mn is the inverse of the G downstairs. The G downstairs in the S1 direction goes like r squared. Its inverse goes like 1 over r squared. Remember, we derived the Laplacian and we wrote it out in terms of covariant, the square of covariant derivatives. There was always a minus sign. That's the minus sign that you're looking at there. Okay, so that's that. And what I'm going to do is I'm going to consider a massless field phi, and it's a scalar. And I'm choosing it as a scalar because a scalar is a scalar is a scalar is a scalar is a scalar. It's always a scalar. So, scalar. And here we go. Here's your favorite equation in 10 dimensions. If you have a look at what the scalars do, you look at the action, it's phi, Laplacian phi with a star in there to be sure that the whole thing makes sense if you write it in there. You've got the fields, you haven't seen the supergravity action, but that's the way it comes. And the equations of motion look just like this. So I want to solve those equations. And the first thing I'm going to do is to use this formula to say that what I really want to solve is dm phi minus 1 over r squared, d squared, theta squared, phi is 0. So this is actually the equation of interest. Right? Okay. Now, the one thing that you do know is that Phi is a function of x and theta. X, remember, is the coordinate on M, and now theta is the only coordinate we've got on S1. And we also know that if this is really a scalar on S1, a real honest scale on S1, it must be periodic. If I send theta to theta plus 2 pi, this should be true, right? Otherwise, there's something wrong. So it's an honest scalar. It's not something else. But any function of theta of S1 like this has a Fourier mode expansion. Voila. The coefficients of the Fourier mode expansion will depend on the coordinates, but basically it's exactly just standard Fourier mode expansion. Now, the great thing about that is I know how to differentiate. So if I differentiate with respect to theta twice, what do I get? Minus n squared. Over there's a minus sign. Right? So for every mode, we get a nice equation, which is that. And that means that we have masses for each mode which go like n over r. So, wait a minute. We started off with a massless scalar in 10 dimensions. But from the point of view of four dimensions, I don't just have massive scalars. I have a whole infinite number, first of all, an infinite number of fields, because this is all, every chap in the integers is allowed. So I have an infinite number of fields, and these fields all have mass, except for n equals 0, which is massless. From your four-dimensional perspective, we've really improved the situation. We went from one scalar field to an infinite number of scalar fields. But the thing that saves us is, as I said, they're all massive. Now, if we make the mass of these fields really, really big, you'll never create them. You know, at the moment, at LHC, we're pounding things of, some incredible amount of energy together. But if we make these have a mass of close to the order of Planck, you're never going to produce them in the experiment. You'll never see them in 4 dimensions. Maybe they're from some on the old universe scenario, but you'll never get them to move, you'll never see them, okay? So how do I make these masses really big? Easy. I let the arc over 0. So the masses become really big, so they fall out of any spectrum that I'm actually interested in. And that answers the question that was raised before. What do I mean by small? Well, that's what I mean by small. The volume of my circle is going to 0. Okay? It's that guy which is going to 0. It's that guy going to 0, which is making all of my states disappear. All of them? Except for 0. You can scale 0 any way you like. It's always 0. So this only leaves on M. So this is the game we want to play. We want somehow to repeat this exercise for a completely arbitrary k. Okay? In general, principle, I would have an infinite number of modes from the perspective of M, an infinite number of fields. From the perspective of M, I'd have an infinite number of fields of very different types, because even if I start with a 2-form upstairs, I get all sorts of nonsense downstairs, right? All towers of them, infinite numbers of them. But somehow I want to crunch K, I want to make it as small as possible, and I want to be left with a finite number, in this case 1, of fields which are happily doing whatever they're supposed to be doing on M. Is that clear? Strategy is clear?
What about n big enough to compensate the smallness of phi?
Doesn't matter. Take any n that you like, and I can always make R small enough.
George, and if you compactify it in a different circle, like you use instead of the circle non-orientable.
Thanks. Well, if it's one-dimensional, I don't have any problems. But no, I'm going to do the same story now with an arbitrary K.
No, I'm just wondering if the mass will be different. I don't know. But
Yeah, no, the masses will be different.
will not be the same as the circle case.
Will not be the same as the circle. Because the spaces that I'm talking about don't necessarily know about circles, so it won't be the same. Okay. Right, guys. So we leave that there. It's not much to do this, so it's nice. Okay. Where are we? Okay, we talked about that. Right. So we're only going to worry about the antisymmetric tensors because apart from the fermions and the metric, the only thing that popped up in the discussion that both Barton and Carmen had were antisymmetric tensor fields, scalars, 1 forms, 2 forms, 3 forms, 4 forms with particular properties. So it's always antisymmetric tensors. Forget spinors for the moment. I'll talk about those possibly tomorrow. Just concentrate on the scalars. And I don't want to talk about the metric because that causes undue headaches, which I want to talk about separately. So what we're going to do is we're going to fix our attention on the antisymmetric tensor fields, and we're going to ask the same question that we always asked. I'm now on X, and I've already made a mistake in my notes. Oh, I know why I did that. Sorry. Yeah. I want to solve this equation. This is the equation that I would get if I was in d dimensions upstairs and I had an antisymmetric tensor field. Then this would be the equation that I would like to solve. Okay? We'll pass in on this guy. Don't forget that I always write this guy as d delta plus delta d, and I should put big D subscripts, right? X, 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 and X. Just so that, because we've got a lot of spaces floating around, we need to be sure which one, who's acting where. So we'll just put X's everywhere. And we'll also impose the condition that star, d star, dp, this is upstairs on X. It's terrible, isn't it? I'll just forget that. That's too ugly. So basically the idea is that you have some, D-forms have gauge symmetries, you compose a kind of a Lorentz type gauge. Remember, for one form, when you have star d star A, this is the same as the covariant derivative. If you do that, if you say 0 is equal to, then that's the same as the covariant divergence of A is 0. It's a gauge fixing condition for a gauge field. And likewise, if you have antisymmetric tensors, they also have gauge symmetry. And what this is for is to gauge fix them. I promised you that at some point in life, I would actually tell you what this thing looks like if you wrote it out in gory detail. So let me do that now. So in terrible detail, this is the following. Yep, very terrible detail. So this B, components of B are totally antisymmetric, rank P, so we have P labels. This guy starts off life in the standard way. But as I told you, it has Ricci tensor and Riemann tensor. That can't be right.
So you said that the third division we have in both because B is harmonic. We proved the last.
Thank you. Good question.
Not for Lorentzian.
Worse, yes. Not for Lorentzian and not for non-compact. Thank you. Okay, so so we have to have this as an extra statement, and it's due to the physics upstairs. So we'll pretend that we're allowed to have. Okay, so where was I? I actually think this is P, everybody. So you can check. Yeah, PR N1 B N2 NP antisymmetrized. The antisymmetry is only on the N1, N2 to the NP. That M upstairs is the first label and it goes. Right? You just raise it using the metric tensor, so you can just lift it up. This is not the end of the story. You get a P minus 1 over 2. And then you get, this is why I never wrote it out before, by the way. There you go. Everything's minus. I think that's P. I'm sorry, I don't have a P there in my notes, but I think it should be P. Okay, so how would you have guessed that this was the right thing to write down? One way to guess is just from this object. Remember, this is star D plus D star acting on the form. Right? Delta is star D star up to a sign. Don't worry about the signs. I'm just worried about the metric dependence. Where's the metric in this game? The metric is here. Here, here, and here. And nowhere else. So you can have, there's a form that's supposed to sit there. This derivative can either act on the metric or it can act on the form. So we can have a situation where we have two derivatives, a derivative on a metric and a derivative on a metric. Or we can have two derivatives on the same metric. This D can bypass that, in fact, right over there, roughly speaking. What are the only tensors that we've got with two derivatives of the metric? Riemann. So there was no choice. Without even thinking, this was about the only thing that for arbitrary coefficients, this was about the only thing that I could have written down. And so then it was just a case of doing a few small calculations to show that these coefficients are actually the right ones. Okay. Anyway, I'll leave this as a homework exercise for when you go home. Okay, and this term in particular here is very easy. It's just this one is just d n dn n2 n d 0. All right. Now, as before, so we're dealing with this. As before, I want to take a metric. So on x, we take a product metric of each space. So basically what I mean by that is exactly what I meant by this. That is, I get some metric which only knows about the first space and some metric which only knows about the second space. Okay? So in components, that would mean the following. Gmn of x comma y would be g mu nu of x and gij of y. So it's a very special case. Why not? I'll do it. It's hot in here. Good. Okay. So in particular, if you calculate the covariant derivatives, covariant derivative turns out to be this. Remember, the covariant derivative that we get from the star operator is the Christoffel symbol, or the Levi-Civita connection. And if you take such a product metric, then they can't mix, and therefore the best that can happen is that you get the covariant derivative on M, and you get the covariant derivative on K. Right? That's the best that can happen, and obviously will happen. Now, what are we trying to solve? Well, we're trying to solve this equation, but because of this, under these assumptions, so these are my assumptions, I get this equation. The metric factorizes, it means the Hodge star factorizes. Okay. It means that everything splits nicely. Okay. You can even see it from here. If the covariant derivatives split and the metric is split, this metric never mixes these two. It's either g mu nu, in which case they're both on M, or it's gij, in which case they're both on K. The Riemann tensor, well, the Riemann tensor comes from the definition of the covariant derivative, which is split. So there's no way that I will ever actually get a Riemann tensor which mixes, right? It can't happen. And therefore, I can deduce that this is actually the right equation. So that looks good. Looks pretty manageable. It looks exactly like the situation that we had before. And remember, for us, BP is actually a function of x and y. X here, y there. But let me try to mimic so what I'll try to do is a separation of variables. To give you an idea of how that might go, I would start with something like a 0 form. Take p equals 0, because that's going to make life easy. So if p equals 0, we have b0 xy. we need the compact space is over here. It's in the y variables, right? Just like over here, it's in the theta variable. So omega 0 of k, let's do this in R just so that nobody is upset, is a vector space over the reals. Do you agree? Take any two functions. Omega 0 says that you have functions. Take any two functions, you can add them together with real coefficients, multiplying them, and they're still inside this space. This is a huge vector space. But nevertheless, I could try to find a basis for this vector space, just as I did over there. Okay. So I can try to find a basis for this vector space, and just it'll be a 0 form, there'll be some label, it will depend on y, and that's it. And then anything of this form can be written just as we wrote over here, over some indexing set, b0, just of x now, call it tilde, then put an I there, and then put a I there, and y. That I, well, in the case of the circle, the I is what I called n, and was over the integers. On compact spaces, you can choose nice elliptic operators to actually find such things that span those spaces. On the circle, it's actually just the Laplacian itself, and in fact, in reality, on these spaces, I actually use the Laplacian, but I don't care where they come from. I just want to say there is a basis. Okay, so we'll just take it for granted. We have a vector space. I take a basis for that vector space. Every vector in that vector space can be written as a linear combination of those basis elements. That tells me that this thing can be decomposed in this way. Because this thing is actually, for every x is in here. So every little x is in there. Okay?
Excuse me, in last equation, I runs from what value to what?
Who knows?
Isn't it?
Yeah. Yeah, for example, here it was over z. If it was a 2 torus, if it was S1 cross S1, I could tell you straight away it would be z tensor z cross z. Right? Things like that. So it doesn't matter, you just have to believe that such a thing exists, and you can actually write things like that. So again, you end up with a situation where, just as we had before, we had an infinite number of components, right? An infinite number of fields on M starting in 10D, or in this higher dimension. Even for a scalar, again, because this is a scalar, and there are an infinite number of basis elements here, we get an infinite number of scalars on M. Okay? Different infinity to the one I was talking about before, but an infinity nevertheless. So we have to try to play the same game. If I do take these to be eigenstates, so for example, if I choose these, like I chose over there, to be eigenstates, like that, then I will get an equation which looks awfully like this.
That looks like Helmholtz equation.
Yeah, except I don't think he was working in 26 dimensions. Yeah, I mean, again, it depends on the signs. As I said, if M was Euclidean, then it would be a heat equation rather than anything else. Anyway, let me get rid of this. So again, we're going to end up with a lot of massive states, mass related to the eigenvalue lambda. right? Is a d kappa of, if I just take this object and stick it in here, then I keep this as dn, but then d kappa acting on this gives me lambda I, omega I. Lambdas over here act like mass parameters for that operator. And so I, again, have a large number of massive states, and the only ones I want to keep are the ones which have 0 eigenvalues. So I want to find the ones which satisfy this is equal to
0.
Yay. Good, no? Now that's an equation you do like, isn't it? Right? Compact space, compact co-space, Laplacian acting on a form is equal to 0. That is ringing bells, at least it should be. So, right, so that's the one we want. Now how are we going to achieve this? Well, we've actually done all the work. So the way we achieve this is I'm supposed to write this, right? Because none of this makes sense unless I'm on a Riemannian manifold. But I have to refine this a little bit, because really what I mean is, I mean M with my metric on M, in a suitable sense, times K with my metric on K. Right? I took the product metric, that's what I used to. So what I'm going to try to do is not to consider the metric that I first thought of, but I'm going to scale the metric. I'm going to scale the internal metric, so I'm going to say GK goes to T. GK, something that we've done before, and we'll do it again. And if we do that, we know how the Laplacian on GK behaves. What happens? 1 over T, right? So we have D, sorry guys, G, K, T is equal to T to the minus 1, D, G, K, right? Okay, that's lovely. I plug it into there. So we're looking for that. And as t goes to infinity, what happens? Nothing. It's terrible. As t goes to 0, what happens? As t goes, remember this is now a mass. As far as m is concerned, this is a mass operator. Okay, m squared. Mass squared operator. And these masses and the only one which is not becoming big is the 0 eigenvalue. So the only thing that survives in the limit So we're down to business now. We're interested in this. And now you understand why I was wasting your time for the first 2 lectures. Because that's really where the physics sits. Well, part of physics sits in here. Now, I have to say a few words. Oh, one more thing. We calculated the volume of TGK goes like T to the D over 2, if I remember it correctly. Where that D is the dimension. So that'll be D minus D over 2. Volume of GK. So the limit is again volume going to 0. We're taking the making these guys infinitely massive is the same as taking the internal space and going, okay? So that's the game. Now, no way. Come on, we've only been here for 5 minutes, surely. All right. Well, we'll see where we get to. It doesn't matter. Okay, so look, this is terrific. You're staring at it and thinking, yeah, enthusiasm. Come on. So this is lovely, but there's a mixing of notation here. Ah, yes. Can't trust the guy with the pen. So, that thing is a p-form on X. That's an operator on K. So you have to be a very bit careful. So let's recall that p-form on X. And as we wrote before, p-form on X is anything but necessarily a p-form on M. It could be a p-form on M, p-1 form on M, p-2 form on M, and so on K, sorry, as well. It's the same. And so this operator changes depending on the nature of this thing here. This is a linear sum of objects. I'll show you next a tip. And what this does to each one of those objects is different.
George.
Yeah.
It's not clear why it's a good game to take this t going to 0, because if you do that, you have infinite mass
Exactly.
particles
Yeah.
in your space time. So
How do you create them?
okay, but
No,
this is
seriously, how do you create them? You can't. Look at how much work it took to create the Higgs. Right? It's almost bankrupted Europe. And that's just, you know, a few lousy GeV, a few hundred lousy GeV. That's nothing. I mean, we're talking seriously heavy Planck mass, for example. Not really. I mean, who was asking the question? Somebody asked if there. I can't tell you what the scales are, but I could, because I'm playing my own game here, I could set that scale, and then the universe wouldn't have enough energy to create my particles. So that's the idea. The idea is I make them so heavy that I cannot create them, that they do not enter into my physics. You can refine this and ask yourself questions like the ones you're asking, but this is the simplest question. So I prefer to tackle something easy first and worry about this. Right, so we need to deal with this in the next 30 seconds. So, how are we going to do it?
So we cannot create them, but in a quantum theory with quantum diagrams,
Yes,
we can integrate.
yes, 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 I agree.
Okay.
And there's a decoupling theorem. Thompson and somebody or other's decoupling theorem. This happens for normal, I mean, for you can show that in a fully well, apart from topological effects, you can show that in a fully renormalizable field theory that if you do things correctly and you have supermassive states, you can push them out, even quantum mechanically. You can take their effect. Anyway, we're a little bit far from a quantum theory at the moment. But it's true, like you said, it's true. Okay. So I'll just repeat what I did for the zero form in general and make a claim and leave it to you to decide whether I'm lying to you or not. So proposition. And this guy, I could have just called it M and K, it doesn't really matter. The only thing I need is that X2 is compact, closed. I don't need anything particular about X1. If X1 is an open space, then these sorts of games are not really available to you unless you tell me something more. If you want your functions to be square integrable, which basically would tell me what happens at infinity for my functions and so on. But as long as I'm only interested in, as long as this part is compact and closed, I can actually deal with this part. So I let B, did I introduce the notation? All right. Hang on to that. I didn't introduce the notation, sorry. So if B is a P-form, on X, then let's start with the zero form. So as we wrote before, it's just this. If I write it as, if I take a one form, I can write it as B mu dx mu plus Bi yi. And then two form, which we wrote before, was B mu nu dx mu wedge dx mu plus B mu I dx mu wedge dy I plus J dx dy I wedge dyj, and so on and so forth. So what I'll do is I'll say that I can write the B1 form as a B10 form plus a B01 form. So 1 on M, 0 on K, 1 on K, 0 on M. The B2 form I will write as B20 plus B1. So likewise, any P form in general, I will write as the sum over Q of B Q equals 0 to P of P, sorry, Q. Okay? Everything's preserved. I mean, it's always 2. It's always a 2 form. So 2 plus 0 is 2, 1 plus 1 is 2. Please tell me 1 plus 1 is 2. All right. 0 plus 2 is 2. It's always 2. Likewise here, Q plus P minus Q is always P. So these are all the possibilities. And Q can be 0 or it could be P itself. So that's it. So here's the thing I actually wanted to do. Okay, so B Q P minus Q can be written as some indexing set. I'm not telling you again what it is. Where this is a P form and this wedges against P minus Q form, and this is just a Y. So these guys, these are a basis for omega P minus Q from this, right? Yeah, P minus Q of the internal space, so that's X2, and I'm doing it over C or R, it's up to you. Yeah. Same argument as before. This is a basis for the vector space. Any vector in that vector space can be expanded in that basis. That's all I'm saying. This index I changes depending on what the form is, but I haven't told you what the index is anyway, so we'll just leave it like that. And in general, that could be you know, discrete, and it would be if you use an elliptic operator to define them, but it could also, depending on how obtuse you are, it would be indiscrete, the index. And so, anyway. So that's fine, except when we, oh, I dropped it out. Oh, sorry. Except we got to the point where we wanted delta k b p is equal to 0. So essentially what that means is, because we can decompose all the forms in this way, if we just worry about what happens for, right, then this is just the sum dq I of x Laplacian on the omega I t minus q forms of k. It's Laplacian of k. Okay? And that has to equal 0. Every term in VP, because they're forms of different degrees, has to be 0. So I must have that this thing is 0. What's the only way that I can make this 0?
That the omega I
are harmonic. So what we do instead, so this implies we should expand in harmonic modes. This is also a vector space. It's a subspace of that space, after all. Sort of. Harmonic forms are forms which have a set, which have an extra property. And the Hodge decomposition told us that we have an orthogonal decomposition of every form into stuff plus harmonic, right? So basically this says, no, do not expand in a basis of this big space, but please expand in the basis of harmonic forms, and then you've solved the equation. So if I take harmonic p forms of, this is a basis for h delta x2, in our case we called it k, so I'll keep it in r, because that's where I want to be. Okay, long story short. The guys that will solve this equation can be written as BP of upstairs, big X. Then we get the sum over all the possible guys, right? Because somewhere I wrote that. Ah, yeah. I can always write it like this. And I should expand these in a basis of these guys. So you keep the Q, and you get rid of the P minus Q, and you put a harmonic form there. So we get. I want you to be able to see this, because this is the formula which is so absolutely amazing. All right, so dp of x. Well, we split it into this kind of mixed degree thing. And then we have the sum over a basis of harmonic forms. If I've got the p cohomology group, what's its dimension? the Pth Betty number, which means how many elements do I have in the basis? P. Pth Betty number's worth, right? Because that's the dimension. I need at least that many basis vectors to span the space. So we get the sum equals 1 to BQ of K. So the Qth Betty number of K. We have a field which has got an index which is related to the internal index. It is a P minus Q form on M. This tells me that it's P minus Q form on it. This tells me how many of them I have. And then I just wedge that against this wonderful basis element, A, Q. And these are the harmonic forms of the Little one. Now, that's it. You should be loving this. If you believe this, of course. So, just all you have to do to get that formula is to take this, shift Q by P, because I used, instead of shift Q goes to P minus Q, and then the sums become whatever they are. So here, so we get gamma, we get P minus Q if you shift Q by P. You get P minus Q here. Okay? And then you sum over all the B's, because that's what the BP can be, because that's the formula that we have over here. So just a combination, you get that one. Okay. The number of fields that you can have depends on the topology. Let me write this out in gory detail. So degree of a form on M and the number of them. Like that. So we have a P form.
How does the fact that the Betty numbers, the P and the N minus P relate?
I haven't used it yet. Yeah, no, but yes. So we take a P form on X. And the question is, what do you get on N? And this formula tells you everything. This formula says that if you have a P form on X, you get one P form on X. Then, as far as P minus 1 forms are concerned, so remember here we have P, and we want to find out how many P minus 1s we have, then that would be gamma 1, right? Which are the number of harmonic forms of H1, and how many of those are there?
B1.
B1. So B1 of K. If we have a P minus 2 form,
B2.
thank you, all the way down to a 0 form, of which there are B, P, K. So, you've actually figured out the spectrum for what happens when you start with a P form in D dimensions. You compactify on an internal space which we call K, you squeeze it, and now you look for the spectrum on M. And the answer is, you end up with a P form on M, you end up with B1K worth of P minus 1 forms, B2K, P2 minus 2 forms, and BPK, 0 forms. That's the physics, meaning at least you see the spectrum. Okay? So, exercise. I haven't given you any homework today, have I?
Yeah, the harmonic.
That was not homework. Okay, so, homework, meaning stuff you're doing tonight instead of going to the bar, is Oh yeah, in the bar's best. Well, if you take me with you, I can help. I might not get it right, but hey. All right, so try the following. Take x10 is equal to m cross k, 10 dimensions. And take the type 2a theory. In type 2a theory, what are the scalar fields which are floating around? Sorry, what are the bosonic fields floating around? You have 1, 0 form, or 10 of them? You have a 0 form. So you have a scalar, you have a vector, you have a rank 2 antisymmetric tensor, and you have a, oh, let's call it B, just to show you that I'm very inventive. A rank 3 antisymmetric tensor, right? Please say yes, somebody who knows. I feel very insecure when I say these things. Alright, so these are our scalars. We're not touching the metric. I haven't said anything about the metric, right? So your homework is to, well, you can take M4 cross K, that's the nice one, of course, but, you know, for some reason, for you, it's more important that your physics is in one dimension. So we could have had M1, so this would be K6, we could have had M1, K9. Just have a look and see how many of these you get. What's the spectrum? This is on X. What's the spectrum? Okay. And the reason I want you to do this is because, surprisingly enough, remember this gives you scalars. You've got a scalar, but this gives you scalars. As does this, as does this. One more thing, just to think about. No. I have to explain something. So, yes, one more thing to think about. Yeah, that one's worth thinking about. Remember, we have a P form on X. P could be bigger than the dimension of M. So it says something about the formulae that I'm writing here. You have to be very careful about how you read these, because you cannot have, well, right, bar. I finished, no? Thank you.
We have some couple of minutes for some questions.
They're hungry.
Just to know, the name of the class is Harabi.
Yeah.
What is Harabi?
I don't know. I was actually hoping one of you would tell me. It's like, it's Ugo's fault actually. I didn't want to talk about Calabria, but okay. Next lecture. K for string theory. Actually, no. Let's do strong statement. I just said to you, let's take some product manifold, and I said, hey, here it is, and that's it. I didn't worry about anything about dynamics, nothing. I just said, I want this manifold, and we're just going to work with it. And if you're working with string theory, you've got to work with what you've got. And what you have in 10 dimensions is a supersymmetric theory. It could be type 2a, it could be type 2b, it could be n equals 1, it could be whatever it is. This is what you've got in type 1, etc. Whatever theory you've got, this is what you have to work with. Now you have to say to yourself, well, suppose I do say, oh, I want this manifold. How do I know that fluctuations won't wreck my choice? How do I know that some stupid effect that I've forgotten to take into account in this full string theory doesn't just say, well, hey, sorry, mate, but no, it's not a product of space. So we have to address that issue. And one way to address that issue, and it's a cheap way to do it, it's the only way I will do it, is to say, well, suppose I have some supersymmetry. Then supersymmetry tends to protect things. And so I will ask that when I'm coming down from 10 to 4, I preserve some supersymmetry. I don't want to preserve all supersymmetry because, well, first it's overkill, and secondly, I believe LHC hasn't actually seen any supersymmetry. So we want to get it. We want the supersymmetry. It's a love-hate relationship. You want it because it stabilizes things, it makes things work, and you hate it because you don't see it. So as a theoretician, you're in love. As an experimentalist, you're in hate. Okay? All right. So, but that's the next lecture.